Hello, everyone, and welcome. The field of solar research has not always shared the same limelight as have other outreach topics in astronomy. For instance, black holes, dark energy, dark matter, close to Earth passing asteroids, cannibalistic galaxies, and so on. Our guest this evening is going to help lessen that gap. Dr. Michael Hahn comes to us by way of the astrophysics department at Columbia University. He belongs to what is known as the Savin Group, under the leadership of Dr. Daniel Wolf Savin. It is dedicated to the burgeoning study of solar physics, of which Dr. Hahn is a senior scientist among his fellow PhD colleagues. The team is also comprised of undergraduates and, interestingly enough, high school students. Included alongside his outreach interests are fly fishing, enjoying family time, and being that of a residential backyard farmer. Won't you please give a big welcome to Dr. Mike Hahn.
Should I?
Yeah,
Switch it over to mine. Huh?
Yep.
Perfect. Okay. So thank you for inviting me. It's a pleasure to be here. When I was young, I did amateur astronomy as a hobby, and I used to go to these things with the Astronomical Society of New Haven. They'd have their talks at Yale, and it was always fun to go and hear things. And it's kind of fun to be on the other side and get to tell you about what I'm doing. So I'll talk about wave heating of the solar corona. I gotta begin the talk by thanking all the people I work with. So there's this is my group at Columbia, and then we have some collaborators at other places. I'll show you some things in particular here from some experiments we're doing with people at UCLA. But none of these people had thanks to the government for the money, of course. But okay, so the outline of the talk is I'll start with an introduction, tell you about the sun and the coronal heating problem. It's kind of two theories for how the corona might be heated. They're not really like in contention. It always means it's got to be one or the other. It's probably some degree of both of them. So I want to tell you about the other one as well, the flares and the nanoflares. And then I'll tell you about the one that I'm more interested in studying, which is the waves, and some experiments on studying these waves in the laboratory that are shedding light on the observations that we made. So for the introduction, you probably know a lot of this, but to say it anyway, right? So when you go outside and look at the sun, you see the photosphere, which is 6,000 degrees. And the main features of the photosphere that you can see are they got the sunspots. I'll talk about that more in a moment. And then sometimes, especially towards the edge of the sun, it has this mottled appearance, which is the granulation. So the sun is, it's a gas and it is boiling. So this granulation is the convection cells, so just the boiling of the surface of the sun. This particular image down here on the bottom is from the Deacon's telescope, which is a fairly new 4-meter telescope they built in Hawaii. So 4 meters just to look at the sun, you get some quite amazing images and data from that telescope. I work with some of that data, but I don't have any of this talk, I think, aside from this picture, which is not my picture, just a cool picture. I do want to explain just a couple of physics things about plasmas that will help understand the sun. So the sun is made of a plasma, which is a gas where the electrons have been separated from the ions. So, all matter is there's protons in the nucleus of the atom and electrons outside. And if you heat them up, they become separated from one another. And so that makes a plasma. So it's a gas of charged particles. In a plasma, the most important force that acts on the plasma is magnetism. So you might think, what about electric fields? The electric field tends not to be too important because you got both protons and electrons in the plasma. So if you put like a positive charge in the plasma, all the electrons will move towards it. It'll repel the positive ones and it gets shielded out. So magnetism doesn't really have this property that shields things. So magnetism tends to be the main force that acts on plasmas. And magnets are caused by electric currents. So plasmas, being that they're a gas of where protons and electrons can freely move around, are excellent conductors. So they both carry currents easily, which makes a magnetic field, and then the magnetic field also moves the plasma around by applying a force to it. And sort of an interesting consequence of this is that it tends to be that the plasma and the magnetic field move together. Uh, so you can understand some of what's going on with the sunspots here. So the sunspots are where the magnetic field of the sun is the strongest. So basically, one side of a sunspot is the North Pole and the other side is the South Pole. We can actually measure that. I guess when I pointed, I picked the wrong ones, but it's the same. So this is a magnetogram, which is a way of measuring the magnetic field of the sun using spectroscopy. So the magnetic fields change the atomic energy levels a little bit, and we can detect those energy shifts in the light. And from that, you can figure out the magnetic field. So that's the sunspots. Then you go up into the corona and you see the sun. This is a picture in ultraviolet light, and the bottom of the screen you can't see. Anyway, this is an image taken by the Atmospheric Imaging Assembly instrument on the Solar Dynamics Observatory satellite, and it shows light from iron 11 plus. So at 193 angstroms from iron 11 plus. So that's an iron atom that's missing 11 electrons. So the reason we know that the corona is 1,000,000 degrees Kelvin is because that's how hot the atoms need to be so that when they collide with each other, you knock off 11 electrons. Right? So this is the diagnostic for the temperature. Um, and there's a few different structures here in the corona we can point out. One is, we call this kind of general, kind of fuzzy, the corona, the quiet sun corona. Uh, and then these active regions, it's a little hard to see here, but they've got a quite strong loops. And those are the regions that are above the sunspots. So you got the North Pole and the South Pole, and then there's the magnetic field lines that are connecting the north to the south. Uh, so those are the active regions. And then these other regions are the coronal holes. Uh, they are regions where the magnetic field of the sun stretches far away into interplanetary space. So the plasma and the magnetic field tend to move together. So the plasma in these looping fields is trapped near the sun. But in these dark regions, if the magnetic field is stretched far away, the plasma is not trapped and it just streams out, and that forms most of our solar wind that comes and interacts with the Earth. Um, so those are the structures. And so the coronal heating problem is to understand, the photosphere is 6,000 degrees, and why is the corona 1,000,000 degrees? And of course, this is the diagram for the core of the sun is like 16 million degrees because that's where the fusion happens that powers the sun. And then as you go progressively further away, the temperature drops, and then suddenly it is increasing again at the corona. We know that the energy source for heating the corona is in the form of all this fluid motion that we see in the photosphere. So you look at all that granulation and you can calculate like how much kinetic energy is stored in moving all that fluid around. Somehow you need to transfer it into the corona. And we think that that involves the magnetic field. So somehow the magnetic field is an intermediary. You store the energy in the field and then you release it in the corona. So there's two ways we know that these magnetic fields can carry energy to the corona. Uh, One is by magnetic reconnection and the other is by waves. So let me tell you about the magnetic reconnection first. The most dramatic kind of manifestation of magnetic reconnection is solar flares and also coronal mass ejections, which I'll show on the next slide. So a solar flare is a sudden brightening caused by the explosive release of energy from this magnetic field. So here's a picture of a solar flare in the chromosphere. So it's just this bright area here. And then here in the corona, you can also see it. You can even see these, if it's a really big one, in visible light. Like I think the very first solar flare that was observed also happened to be one of the largest, was seen by Carrington in the late 1800s. And he was looking at sunspots and suddenly it became bright and he was like, wow, that thing. He went to go tell someone about it. When he came back, it was over. But you know. So that's what we call the flare. And then the coronal mass ejection tends to accompany flares. There's a little bit of a debate in so like, do you need a flare to make a CME? Sometimes there's like these stealth CMEs that seem to come out where someone hasn't seen the flare, but generally they occur at the same time. The CME is an ejection of material that flies off the sun and off into space, and often it comes and hits the Earth too. So this is a picture from this is one from last May. So this was one of the CMEs where I think there were some, for the past year there's been quite a lot of these things, and this was one I think caused uh, one of these things that made the news where they said you should go out and try to look for the aurora. So this is one of the ones that caused it. So here's basically what the sun looked like before it happened. Now this is a coronagraph image, so the sun is like a little about half the size of that disk. So it's somewhere hidden in the middle there. And these kind of radial lines that you see, that's the solar wind streaming out of the sun. So near the sun, there's these loops, but the parts that get away from the sun is has to flow along magnetic field lines that stretch out. So it's like the coronal holes and other parts at the top of the loops get pulled out. But so this is showing the flow of the solar wind, which is streaming away from the sun in all directions. And you can see it's a little bit stronger in some places than others, but basically this radial solar wind. And then here, like 20 minutes after this picture, you can see this bubble, which is this CME that has occurred. This one's kind of shooting off to this, but I guess the front of it must have come, it's expanding in all directions. Um, some people who study CMEs, one of the things that they do is try to figure out which direction it's actually going, because it's a little hard to tell just from a plane of sky image. You don't have, you know, people would like to have more satellites to get some triangulation on these things, but anyway, so that's the coronal mass ejection. I put some movies in the great thing about solar astronomy is that you can make movies of things. So, the black hole people don't have movies, but we do. So, here's a this is that's what yeah down here in the lower corners where a flare was going to come off, and you can see that it ejected some stuff, and then there's these loops that form after the flare. So we call those the post-flare loops. So this is just there's this magnetic reconnection continuing to happen, and it's forming magnetic loops below where the reconnection is. I'll let this play. It's fun to look at. And it'll show you some other wavelength bands in a minute too. And there, you can also see there's also like small flares happening in these active regions all the time. So that was a big one. Here it is again. You see some stuff come off in a second. There's the CME. Brightens up, and then you see all this structure of stuff kind of falling down. That's like material from higher up that cooled down and then fell. To get an idea of the timescale of these images, the frames here, I think they're like 30 seconds per second, whatever it is to make a movie. But the telescope takes a picture of it close. It's sped up from reality, but not too much. We are fairly a few minutes over. Very pretty to see the post-flare loops form. These are different temperatures in the corona, and this one's more than chromosphere. You have a high focus. I mean, here in this one, they kind of overlay all the different colors, all the different structures of what's happening. So what's the science of what's going on with these flares is this magnetic reconnection, which I've been talking about, but didn't actually explain what it is. So in a plasma, as I was saying, when the plasma and the magnetic field move together. So suppose you take two oppositely directed fields, like a field that's pointing north, and on the other side, one that's pointing south, and you push the plasma together. Like you can apply pressure, say, to both sides and just move the plasma together, and the magnetic field gets dragged along with it. Now, when you have a region where there's a strong change in the magnetic field, it makes a current. And so that's what this diagram is showing with these X's. It's saying that there's a current going kind of into the board direction here. And when you get to a region of strong current, this approximation that the field and the plasma move together breaks down, and then the field slips through the plasma, and it reorients itself. So you've got these up and down pointing fields, and then they get pushed together enough that they make a strong current and then snap, and they reconnect into what is a lower energy configuration, and the excess energy from the magnetic field gets released. That's what's causing these flares. So here's a diagram of how this works with the flares, that you have some magnetic fields and they form sort of a pinch here, which is like this diagram of the reconnection. Some of the energy from this pinching goes down, and that forms these loops underneath. Like you see these loops kind of contracting underneath. Those are those post-flare loops, and all the energy that goes down hits the photosphere, and it excites all the atoms there and makes a lot of light, and that's the flare. The stuff that's going up, it doesn't have anything to hit, so it just keeps going, and that forms the CME. So that's the basic picture of what's these flares and CMEs. Now the connection between this and flare and CME and coronal heating. One theory of coronal heating is that this happens, we see the big ones pretty clearly, but maybe it happens kind of all the time on a small scale where we can't really resolve it. And this is called the nanoflare heating theory. So this cartoon is from a famous paper by Parker. The same Parker that they made the Parker Solar Probe named after. So he did a lot of things. He predicted the solar wind, and this nanoflare theory was his invention. And so this is supposed to be like one side of a loop of magnetic field on the sun, and this is the other. So you just straightened them out for the sake of making the diagram. And as the flows in the photosphere move the fields around, they get tangled up. And then you'll have lots of places where the fields cross each other, and you form these X points where you can make those reconnection points. On the right is an image from a very high resolution. This was a rocket experiment that someone did. This is my paper. I can't even remember where it's from. Williams, but it's covered up. But not my work. But it's still a really nice picture. And they did some photo processing to it too to bring out the structure. But you can kind of see there's a good argument that some places in here you can see like some twistiness. People argue, is there really enough? What is really the width of these strands? Are we resolving things or not? But that's the idea of the nanoflare theory, is that you've got these strandy magnetic fields that are getting all twisted up. I think most people think that this is probably probably works best in something like an active region. Like here, this is an active region. There's a sunspot below what we're looking at here, and you have strong twisted fields. But what about maybe in the quiet regions? It would be a little harder to do this. And in the coronal holes, it's open, so it wouldn't really work in a coronal hole. So that's the nanoflare idea, though. I work more on the wave heating idea. So I'll talk about that now and show you some observations of waves. So the particular kind of wave that I'm interested in are these waves called Alfven waves. Where's my... Oops. I'm trying to hit the play button, but let's see. Yeah. Oops. But I'll just play it with it being small for a moment. So this is a movie from a different satellite called the Hinode satellite, and they're looking here at the chromosphere actually, but so the corona is up on top. And these Alfvén waves are waves in which the plasma and the magnetic field move together. It's kind of like just a wave on a string where you shake the string and it wobbles back and forth. These structures that you see at the bottom are called spicules. They're just little bits of magnetic field that have a little more density than the stuff next to them for whatever random reason. And they're doing a lot of things. But one thing you can see that they're doing is that they're waving back and forth. And these are Alfvén waves in the chromosphere. And then on the next slide, I have a movie also. This is a movie of actually the corona. So in case you wonder whether they actually make it up into the corona, we can see them here. This is from that SDO satellite, the Solar Dynamics Observatory again. And what they did in order to highlight motion was they took from each frame of the image, they subtracted the previous frame. So that way you highlight things that are moving. And if you look, so here's the edge of the sun. And if you look at the kind of above the sun, there's like these radial lines. Those are the magnetic fields. And it's kind of subtle because the sun is huge, but they're gently waving back and forth. So they're moving many thousands of kilometers, but it doesn't look like that to you. Maybe not thousands, maybe 10,000, but 10, yeah, okay. Was it 26? 10 kilometers, 10 or 20 kilometers, maybe. Anyway, so that there's the waves going back and forth. And there's also other things happening. There's little jets forming. It's kind of fun to see all the little activity that happens. But the idea is that there are plenty of these waves in the corona. So waves are found throughout the corona. And if the waves are damped, then they can heat the plasma, right? The waves carry energy with them, but you need to get the energy back out of the waves somehow. So that's actually turns out to be more difficult than just finding the waves. Like we know there's tons of waves, but how do you actually get the energy out? Um, Collisions can damp the wave. So basically like the viscosity or the resistivity of the plasma, but that turns out to be kind of slow. Like they won't dissipate just from viscosity until they get like 3 solar radii away. And by then they're not really near the sun anymore. They won't do any heating of the corona. They might push the solar wind around, but they wouldn't heat the corona. Um, so you want to really get them to dissipate below 2 solar radii. So one thing that we did was to look, we don't know why they're damping or not, but we wanted to see, do they damp, right? So this were some measurements that we did some time ago. This was using spectra from this instrument, the Extreme Ultraviolet Imaging Spectrometer, which is on this Hinode satellite. It's a Japanese mission with collaboration with NASA. It's getting a little old now. It's from 2006, but it still works. You get good data still. This is obviously not the real picture of it because it's pointing the wrong way, but that's yeah. And it looks at the extreme ultraviolet. So it's a slit spectrometer. So when you look at a spectrometer, you have like one slit, one direction that measures the spatial direction, and then at every point along the slit, you get a spectrum of the light as a function of the wavelength. So for this particular observation, we looked at 4 places in a coronal hole. Coronal holes are nice and simple because the field lines just go straight away. So that seemed like the nicest place to try to study waves because there wouldn't be a lot of like, complicated structure of everything's kind of straight and radial. To get good data, we added these up, and they go to about 1.4 solar radii. The radius of the sun, just for scale, is about 700 million meters. So there you go. So at every pixel there, you get a spectrum. You got intensity versus wavelength. This is, I think, about a quarter of the spectrum. ICE looks at a lot of iron lines. Iron, I'd say why iron? Because the sun's mostly hydrogen and helium, but iron is, I think, about 1 in every 100,000 atoms on the sun is iron. So it's not a lot, but iron is a complicated atom. It's got a lot of electrons in it, so it has a lot of atomic transitions. So in the corona, it actually produces a lot of the light that you see, and it makes a good diagnostic because here you've got, this is iron 9, which is iron that has lost 8 electrons, iron 12, iron 8, iron 11. So you see all these different charge states of the iron, and by measuring the relative amount of each kind of species of charge, you can figure out exactly how hot the corona is because it's losing those electrons because of its temperature. So they designed this instrument to measure the temperature very accurately by using those different charge states. But we didn't use that. We do in some ways, but the main thing here for looking at the waves is we're looking at the shape of the lines. So if you zoom in on any particular spectral line, this is the iron 12, 192 angstrom line. So it's in the ultraviolet. Intensity versus wavelength again, and the histogram here is the data. But you can see it's got a width to it, which we can fit and approximate as a Gaussian, and then you can figure out what that width is. There's also some instrumental effects we account for. Now, what causes this to have a width? This is basically the Doppler effect. I'm sure you know about the Doppler effect from redshift and such. So when you have just random thermal motions, the air, the temperature is proportional to the kind of speed of the particles in the air. So part of this is broad just because of the temperature of the plasma. So it's the random motion of the ions moving towards you and away from you broaden the line. But it's actually broader than from the temperature alone. So there's this additional broadening, which we call the non-thermal broadening, but it comes from the waves. So as the waves are moving, sometimes they're sloshing towards you, and sometimes the wave is sloshing away. And so it's this Doppler effect of the wave shaking the plasma around that is broadening these lines, in addition to just the random kind of microscopic thermal motions of the particles. And so you can extract the wave amplitude. We say it's about twice this non-thermal velocity. The reason for the factor of two is sometimes the waves would be going, this way from your perspective, and sometimes they're going towards you and away from you, but you only see a Doppler shift, they're moving towards you and away from you. So multiply by two. So it's you can prove that mathematically, but that's the reason for the two. So the measurement we did was we measured this non-thermal velocity, which is essentially the wave amplitude, as a function of distance from the sun. Now, if the waves were not damped, these wave amplitudes would follow this dashed curve. And that's because that's what would imply that they're conserving energy. You'd say, why do the waves get bigger as they go away from the sun? Well, the density of the sun decreases. So the energy in the waves, like the mass times the velocity. So as you go away from the sun, there's less plasma and less mass. So this velocity increases if the energy were conserved. But our actual measurements of these wave amplitudes, initially it kind of follows that, which is nice, and then it falls off that curve. So somewhere around 1/10 of a solar radius, we're losing the energy from the waves. So we see that the waves do lose the energy that they have. You can also estimate how much energy is in the waves, and some other people also did this. So it's probably right. Um, but anyway, so the waves, you can estimate the energy in the waves and show that they're dissipated near the sun. Uh, so that makes wave heating a very plausible mechanism. And we still want to understand, though, what is the process that actually damps the waves? Like, why do they lose the energy? Which is more of a plasma physics question about what the behavior of this kind of wave. So in order to study that, we've been doing some experiments. So I'll tell you about the experiments. So don't have too many equations, but so this is a picture that I said before that these waves are basically like the same as a wave on a string. You shake the wave, that you just like shaking a string, and the wave travels along the string. So these waves are like you shake the magnetic field with the plasma on it, and it wiggles back and forth. And if you yeah, so if you remember, if you had physics, then you might, maybe, I don't know, my students might not recognize it either. This is the wave equation for a wave on a string, and it's the same as the wave equation for an Alfven wave. So this is like describes the oscillation of the magnetic field, and this is the speed that the wave would travel, which is the background field divided by the square root of the density. So this is an approximation that is valid at low frequencies and long wavelengths. So that's one of the reasons for doing the experiment, is how good of an approximation is it under like solar conditions. So we got these waves. So one idea is just in the same as what if you think of a wave on a string, if you have like a light string and then a heavy string, and you shake the light string, the pulse will get to the heavy string, and then some of the pulse will go forward. That's the transmitted wave, and some of it will be reflected. That's the reflected wave. And since the Alfvén waves are analogous to these waves on a string, only instead of tension and the density of the string, it's magnetic field and the density of the plasma. Maybe it's because we have a change in the medium, in this corona that they're traveling in. So you've got, like, you're going from like heavier plasma near the sun to lighter plasma further away, and the stronger field near the sun and less magnetic field far away. So you've got a change in the properties of the medium, which could reflect the wave. So we wanted to measure how do waves reflect when they encounter a change in the medium, in the wave speed. So we did some experiments at the Large Plasma Device at the University of California, Los Angeles. So here's a picture. Let me go back. I'll just talk about the picture for a minute. So this is a 20-meter long cylinder. I'll show a video too, so you get a sense of the scale of it. So it's a 20-meter long cylinder. Over on the left side here, there's a cathode. So it's just a piece of metal you can make very hot, and then you apply a high voltage to it, and you can make a spark that will travel down the device. So it makes a big spark, and that's the plasma. And these yellow and purple things are coils of wire. So you make electromagnets, so you can control what kind of magnetic field you want to have the plasma have. And there's all kinds of ports here where you could insert different things. So we're going to put an antenna in somewhere, and we'll put in some probes to measure the waves that we make. It's really a very versatile device. And kind of the nice thing about it is that one nice thing, it's very well designed and versatile, and they operate it as a user facility. So if you are like me, an astronomer who has an idea for some experiments, you don't need to build your whole lab. You can, talk to them and say, can I come there for a couple weeks and do some experiments on your device? And they'll help you out. And then it's been quite a nice collaboration. Um, so our goal here was to try to mimic the sun, at least in the sense of having Alfvén waves that encounter a magnetic field like the one in the sun. So this is a plot illustrating how the Alfvén speed changes as a function of distance above the sun. So the Alfvén speed is this thing that was the speed of the wave, which is the magnetic field divided by the square root of the density. So this encompasses the relevant ways in which the plasma is changing with height. Um, and then I did something a little tricky here is I normalized the x-axis instead of like distance in terms of like meters, I've normalized it by the typical wavelength of an Alfvén wave, right? Which is they're about 1 solar radius in wavelength. They're very long wavelength waves. In the laboratory, we can set up the magnetic field in this device so that our Alfvén speed is a function of distance along the plasma will have a slope in it, a gradient that looks very similar to the one in coronal holes, as long as you agree that we can normalize the distance here by the wavelength of the wave, which instead of 1 solar radius, we obviously can't make a wave like that, but we can make one that's a few meters long. So it's we're scaling things down to a laboratory scale, and we think that this is the relevant quantity is the kind of length scale of the gradient relative to the wavelength of the waves we're trying to send through it. Yeah, so we're going to make that the same. So this is the experiment one of them that we did. So we put an antenna in the plasma. I should talk about the magnetic field first. So we've got a magnetic field that goes from a low magnetic field, and then we can step it up to different stronger magnetic fields. We can make a step in the magnetic field, and we would expect that at the step, some of the wave will go through, and some of it will be reflected. So we put an antenna on the low field side, and we shoot waves toward this step. We've got some probes here called B-dot probes, which measure wave magnetic fields. We put a couple before the gradient and a couple after it. That way we can measure how much energy there is before it hits the gradient and how much goes through. And then we can try to see how much energy gets transmitted. This is not as good a movie as the NASA one. I just made this on my phone one time when I was there. So but just to get an idea of what the lab looks like. There's this spark. It only lasts a few milliseconds, but the waves a few times that in order to fit waves in the machine. And then I don't know, there was other devices for probes and things. And then, so this is the kind of data we get from this. The way we make these measurements is we have a probe that measures the magnetic field of the wave. So we put this probe on a mechanical drive that is automated by the computer. So it'll make a measurement in one spot, and then it'll move to the next spot and make a measurement again. And the experiment's very reproducible. So every time you make the spark, you make a measurement. Maybe you do it a few times to get an average, and then you can move your probe, and it's doing the same thing every time, even though it's a different plasma, because it's very reproducible. So that's how we've built up these plots. So this is a measurement through a cross-section of LAPD, the large plasma device. And this is showing the magnetic field. So you see the magnetic field pointing up, and then it points down. So that's our Alfven wave, um, shaking the plasma around. This was built up. You can see there's many measurements building up. So when we go there, we set everything up during the day, and we usually press the button at like 6 o'clock, if we're lucky, 6 o'clock, sometimes more like 9 o'clock at night, and hopefully everything works. And then we go home, and then come back in the morning, and hopefully there's data. So that's the way it works. And then so the left side is the waves before the gradient, and the right side is after the gradient. And one thing you can see is that the waves do lose energy as they go through the gradient. So the color scale shows you the magnitude of the magnetic field, which is larger before and smaller after. So we have lost energy. And then we can figure out how much energy they lost. So this is the ratio of the energy in the waves before the gradient, after the gradient, to the energy before the gradient. So how much energy is transmitted as a function of, this is the wavelength divided by this LA. So this is kind of like the steepness of the gradient. So remember, we wanted to normalize the length scale, by size of the gradient divided by wavelength of the waves. So this is that. The sun is around here. It was like 4.5 for the gradient in the low corona. And so you can see that when you get to about 4.5, only about 15% of the energy is going through the gradient. So a lot of it is getting reflected and it's getting trapped near the sun, which presumably helps to trap it near the sun, and then it gets dissipated. We think actually that the reflecting of it is important for dissipating it too, because there should be when you collide waves traveling in different directions, it generates turbulence, and this is going to be an effective way of dissipating the energy from the wave. So the reflection is probably important. This was the work by my postdoc, Shayak, actually, so I should give him some credit here. He did a very nice job. We got one thing you might want to ask is why does 50% of the energy get lost even when there's no gradient? That's because in the experiment there is more collisions in the experiment than there is in the sun. So we try to match the sun as well as we can, but there will be some differences. So one thing here is we do lose more energy from collisions than would actually happen in the sun. So one question that we aim to address in our continuing work is, does this change anything else about it? Like, is this really representative of the sun? Should we expect the sun to do the same thing? We think not, but of course that's a question that needs to be addressed. The other thing we can do is we can measure the reflection of the waves. So this same idea, we're going to have an antenna and some probes before and after a gradient. The after the gradient ones, in this case, since we're looking for reflection, are mostly just to kind of monitor the wave, what goes through. But our main goal is to look for a wave coming backward. So the idea here is you start the wave at the antenna, and then it's going to be observed by probe number 1, which I'm going to show in blue, and then it'll be observed by probe number 2, which I'll show in red. Then it'll hit the gradient, then it'll come back, and you'll see it on the probe number 2, the red one, and then the blue one. So the order at which it hits these probes will reverse if there's a reflected wave. And here's our reflection measurement, which you see the blue probe, which is the first one. The wave shows up here in blue first, and then it shows up in red. And then after the pulse ends, you don't see anything for a little bit. And then there's some kind of weak wiggles out here, but that's a reflected wave where you see the red signal before the blue. So we found a reflected wave. I don't know if you noticed, but this paper is 5 years after the previous one. It was actually a little bit of a challenge to see the reflected wave. So it was it's one slide, but it was a lot of work actually. Part of it was those collisions were stronger in previous experiments, and if you make the plasma hotter, you can get less collision. So we actually made the plasma a bit hotter, and we're able to finally see these reflected waves because they were getting damped out before we could measure them in the other experiments. But anyway, so of course this has implications for the sun. We can now see that gradients on the scale of what we have in the corona do reflect waves. This probably helps to make turbulence in the corona, which can lead to coronal heating, and but there's also other applications for understanding Alfvén waves. So I just say a few other things about it. So we got Alfvén waves are important in fusion devices. So you might know that people want to confine plasmas using strong magnetic fields and then heat them up. And then if you get them hot enough, the particles will collide with each other enough that they'll fuse together. So you would make a hydrogen plasma or like deuterium and tritium and then smash the atoms together. So this actually needs to be hotter than the center of the sun. Like the sun has gravity to pull everything together, but if you want to do this on Earth, you need to make it hot enough that they'll collide with enough energy to undergo fusion without being able to rely on gravity to like force the atoms together. So that's a big area of interest right now is fusion. In fact, there's been like developments in making superconducting magnets, so that now there's a lot of like companies that are starting like fusion companies to try different concepts for generating energy, and it's looking more promising than it has in the past. It used to be a thing. Fusion's always 30 years away, but it might be less than 30 now for a change. Uh, Alfvén waves also affect the aurora. So there was some experiments, actually experiments by other groups who were using LAPD recently, where they showed how Alfvén waves can accelerate electrons under conditions that are relevant to forming the aurora on Earth. So when the solar wind interacts with the Earth's magnetic field, part of what's happening is the particles are getting trapped and they're flowing down and hitting our atmosphere. And part of what's giving them enough energy to make the atmosphere glow is that there's also alpha waves coming along with them and pushing the electrons around to give them some extra energy so that um, they make the nice aurora that you can see. And then one more place. There's lots of places in the universe where there's Alfvén waves, but one more is around Jupiter. Um, so Jupiter is when when the Earth interacts with the solar wind. Maybe you've heard that there's a bow shock in front of the Earth because the Earth is actually traveling faster than the Alfvén speed in the solar wind near us. So it makes a shock. Like the speed of the Earth is supersonic, super Alfvénic compared to the solar wind here. For the moons around Jupiter, though, their speed as they orbit around Jupiter is less than the Alfvén speed of Jupiter, and so they interact with the magnetosphere of Jupiter in a different way than the Earth interacts with the solar wind coming from the sun. So it's like um, this. What ends up happening is that particularly Io, Io is, as you know, is very volcanic and it makes lots of particles. It's always spewing out into its atmosphere. These things get ionized in the magnetosphere, and then Alfvén waves help to transport some of those charged particles to Jupiter and make little spots on Jupiter that are kind of like a Jovian aurora. They call that the Io plasma torus and these Alfvén wings that lead to the aurora on Jupiter. So there's lots of places these Alfvén waves play a role in astrophysics and in artificial plasmas as well. So to summarize then, plasma waves probably do most of the heating of the corona outside of active regions. That's a little bit of an opinion, but I think especially in coronal holes where you would have trouble twisting up the field, I think it's the Alfvén waves that do it. We've seen the Alfvén waves; they're everywhere. They carry a lot of energy. We observe that they dissipate near the sun. How the energy is transferred from the waves to heating is not entirely clear. We do show that they do tend to be trapped near the sun, and it's probably this reflection of Alfvén waves and interaction with outward traveling Alfvén waves that is leading to the energy becoming dissipated. And our experiments support the hypothesis the waves are partly reflected and are trapped near the sun. So thank you for your attention.
All right. Paul's going to bring the house lights back up and we can take questions if there are any questions in the room. I'll be monitoring the chat also, see if we have any questions out there.
Sure.
Mechanisms for how flares. Just want to see if I got it right. You have magnetic fields supporting material, right?
Mm-hmm.
Something pushes the magnetic field together, it pinches them off.
Yeah.
All that material drops and it basically heats up the photosphere.
That's right. So what pushes them together isn't always clear. So one thing that people who study flares are trying to do is figure out what triggers this to happen ultimately. Sometimes it seems to be like new magnetic fields arising from underneath the photosphere that you can't see and pushing stuff that already exists closer together, something like that. Um, but once you form one of these X points, we call them, then you get the magnetic reconnection, and that sends energy downward that hits the photosphere, and that makes the light, and then the kind of bubble at the top flies off into space, and that's your CME.
Idea, perhaps I know this still around, that sound waves heat up the corona, not that it's coming from the photosphere.
Yeah, I think it's true that that used to be an idea that sound waves could do it, but sound waves, it turns out, do not have enough energy to do it. So it's not sound. We think sound waves might play a role in heating the lower layer of the sun, the chromosphere, actually. That's still possible. It might not be quite enough, but there's still something for them to do. But the Alfven waves are capable of doing the corona. You can measure the sound waves too. So with the Alfvén waves, what you measure is the Doppler shift of stuff moving towards you and away from you because it's shaking the magnetic field around. Sound waves you measure because sound waves are they make the plasma denser and then less dense as you compress the air, and so you can actually see them as like traveling little density compressions. So we can measure the sound waves as well, but they don't carry quite as much energy. Did you have a question?
No, I was looking at the Soho picture.
Oh, okay.
So now I know the white and dark areas on the magnetogram. Now I know which ones are plus, which ones are north and south, so I can add that to my.
There's a nice website you can try, a Helio viewer. You've seen that one? It's does this have the internet?
It does.
So we can have fun. I like this one. So let's see, data sources. So it's pretty up to date, and you can look at, so here's like the SDO images. So some of the ones I was showing would be like this one. Um, yeah, so what is this? This is AIA ones. And then you can look at the go to this other instrument and you'll see the sunspots. What day is this? 2026. So this is this today? Show me the newest one. February 13th at 23. Yeah. So this was kind of set up as part of an outreach thing, but also I think a lot of researchers use this to try to find interesting things happening on the sun. So I find it fun just to look at it sometimes and see what the sun is doing. But so I recommend if you're looking at things, I recommend it. It's quite nice.
Thank you.
So there are a couple questions in the chat.
Sure.
So, is the sun unique as far as superheated corona, or do all stars have this?
Yeah, I think most stars have hot coronas. We know that most stars have magnetic fields, and so they probably have similar physical processes to the sun. So you can measure the temperature of other stars in their corona. So do all of them is a little bit categorical. I'm not sure I could like apps promise that every single star has one, but certainly there's a lot of them that do have hot corona. The sun's not the only one. Little like what you can do with other stars is one thing is you can see the star spots on other stars. When people are looking for exoplanets, one way that they look for exoplanets is to look for a dip in the light from the star when the exoplanet goes across. And in the course of looking for these exoplanets, they actually ended up observing tons and tons of star spots. In fact, the exoplanets people are kind of annoyed about it because they don't want to see the star spots. They're looking for planets. But it's been great if you're a stellar astronomer because then you've learned a ton of stuff about magnetic cycles on other stars and star spots. So we know they have star spots, and we can kind of, how many spots they have is a good proxy for how strong the magnetic field is. younger stars have stronger magnetic fields. These little red M dwarf stars have, quite strong magnetic fields actually. And so that tells you about the kind of energy they have available for heating. And then you can also look at the X-ray emission from other stars, and those X-rays are tending to come from their corona, and that gives you an idea of how hot the corona is. How much X-ray light that they're making. So they do have coronas in other stars, yeah. And they're probably heated the same way the sun's is because we know about the magnetic field. So there might be differences. Oh yeah, okay. What else we got? Do iron lines have different sensitivity to magnetic fields? So yeah, so if you want to, so people, yeah, how to measure the magnetic field of the sun is like there's people who are interested only in that and coming up with new and clever diagnostics to do it in different ways. These magnetograms that I was showing, wonder where they're I can yeah, like the magnetogram here. So that magnetic field is being measured in the photosphere. So you can't use these highly charged iron atoms to measure that because they're too hot. Those are way up in the corona. These are actually being measured using neutral iron that's in the photosphere. And so there's certain atomic transitions in neutral iron that are good for this. But other elements also have good transitions. I think there must be a reason that they chose iron. It's probably has the widest separation line. What happens is that when there's a magnetic field, normally you'll have one spectral line that gets emitted, but in a magnetic field, the atomic states split, and so you'll get a doublet of spectral lines instead. And if you measure how far apart in wavelength the doublet shifts, then you can measure how strong the magnetic field must be. And there's also some tricks with polarization that you can do. Uh, People would very much like to measure the magnetic field directly into the corona, which is a bit more challenging because the shifts in the wavelength that you get are smaller um, for these highly charged lines because they're in the ultraviolet, so you're already looking at small wavelengths, and the shifts are even smaller than that. So you need very high resolution. But that's kind of an area of research for spectroscopy is to measure magnetic fields directly in the corona. Right now, if you want to model the corona, you measure the magnetic field in the photosphere, and then you use a numerical model to try to extrapolate what it does higher up. And then what else was here? The first picture of granulation looks like snarling little faces, and the loops of the corona seem more vaporous. Is there a direct connection between the two? Yeah, so how the magnetic field gets from the photosphere to the corona is kind of complex. So if you zoom in on this magnetogram, you see the magnetic field isn't evenly distributed. It's got these like concentrations, and if you look at, they kind of are at the edges of their own like convection cells, and it might be hard to tell, but these convection cells are bigger than the granulation convection cells. So we call these supergranules instead of granules. And why exactly you get these larger patterns is it's not completely clear. It has to do with the flows in the photosphere somehow that at the height at which it pushes the magnetic field around is a little lower down, and so it forms these bigger cells than the ones you see at the very surface. Um, and most of the loops that you see in the corona are coming from these concentrations that are at the edges of these supergranules. So the magnetic field in the sun, even though there's a magnetic field everywhere, the parts that make it the highest tend to come from these concentrations, and they form like a funnel-like structure where they're very narrow at the bottom, and then as you go up in height, they suddenly get much wider, and then they fill up the whole corona. So they got to, you know, yeah, so they call them funnels. Yeah, so there is a connection, but finding how the magnetic field goes from, tracing it is you can do it. People do that, but it is, it's not completely straightforward that you could just do it looking at a picture. There's some complexity to it. What kind of data or measurements are you personally looking forward to receiving from Parker Solar Probe? So with Parker Solar Probe is there's lots of interesting things you can do with it. One thing that is interesting is you can make the same kind of measurements of the waves that we do in the laboratory, basically. So, when we're looking at the sun, we have to use spectroscopy and measure Doppler shifts and infer something about the waves that way. But when Parker Solar Probe is actually in the corona, so it has the same kind of detectors on it that we would stick on our laboratory plasma. So you can measure the waves directly at a point. So a problem with spectroscopy is the corona is what we call optically thin. You probably know this. So you're seeing you see straight through it, and everything along the line of sight adds together to the total amount of light you're seeing. So it kind of washes out some of the structures, and so it's a little bit hard to tell exactly where the light you're seeing is coming from. Um, Whereas when you have an actual probe that you put in there, you know that the measurement you're making is at this exact particular point. So you can get some very precise data using like an in situ measurement, and it complements the spectroscopic measurements we have. So I'm looking forward to doing some measurements with Parker Solar Probe of the Alfvén waves. And one thing we've been looking at is how Alfvén waves interact with sound waves in the solar wind. So we think um, in the experiment, as I told you, the Alfvén waves get reflected from changes in the Alfvén speed, which depends on magnetic field and density. Well, sound waves create a kind of they create changes in density, right? Compressions and rarefactions. And so if an Alfvén wave is running into this kind of corrugated density background, that should tend to reflect the Alfvén waves. And there's also other interactions that you can get between the Alfvén waves and the sound waves that might tend to increase the heating rate or do even kind of new sorts of wave phenomena. So we're studying that actually. It's quite interesting, I think. What was the point for that gradient within the experiment? Also, another slide showed the wave speed increasing as a function of distance. Why that increase? All right. So let's see. I suppose the one that showed an increase was this one, I'm assuming. You can let me know if I've got the right interpretation. This wasn't showing wave speed, so this V, okay, I should have labeled it better. This is this non-thermal velocity, which is like the amplitude of the wave, like how fast the wave is shaking the plasma. But that's different than the speed at which the wave is traveling, right? So like if you shake a string, then it's gonna move the string up and down with a certain speed, but there's also a speed at which it propagates along the string. And so when I talk about the Alfvén speed, that's like the speed of propagation, like how long it takes the signal to get from one place to another. This one here is more the amplitude, it's like how fast the plasma is shaking, right? So there's kind of two different speeds associated with the wave. And then
Excuse me.
what was the other,
There was another
what
slide
was
that
the point
showed
of the
the
gradient
increase.
within the experiment? So in the, so we wanted to make an experiment in which this Alfvén speed changes in a way that is similar to the way it does in the sun. And so that was the point, was make it match the corona as well as we can, at least in terms of the size of the gradient divided by the wavelength of the wave. And then what else we got? How did they determine how long it takes from the center of the sun to the corona or surface? How did they determine how long it takes? How long? I'm afraid I don't understand that one. How long it takes?
I think she might be asking it, but there's something that says that it takes a really long time for a photon to get from the center of the sun out to the corona. I think that might be what Louise is trying to get at there.
Oh, okay. Yeah, I think so. Yeah, I don't know if nobody's actually like literally measured that, right? But that's a calculation based on the density of the sun and thinking about so when an atom emits a photon, like if it was just in a vacuum, the atom would just go straight to your eye or wherever you're going to observe the photon. But in the sun, it's very dense, and so an atom will start from it'll emit a photon of light, and then there's an atom right next to it that'll collide with it. So you can, based on the density, you can kind of figure out how many collisions the light will have to go through in order to get all the way out. And every time it bounces off an atom, it will get emitted in some other random direction. And so there's a kind of a statistical calculation you can do to see, how long would it take to go out. It's a little bit like, so another thing that's sort of similar to it. I don't know if you'll think it's similar, but it comes to mind, so I'm going to say it anyway. It's like, think about electricity, right? When you turn on the light switch, the lights turn on immediately. But if you think about the electrons traveling in your wires, they travel at like less than a millimeter per second. Like, so they don't actually like flow through the wires like water in a pipe. The electrons shift a tiny little bit, and it actually would take like a single electron that started off at the light switch hours to make it to the light bulb. So that's just, but maybe that's a similar sort of thing, just because they tend to bounce around against all the atoms in the metal. Makes sense.
We have time for one more?
Sure, yeah.
Okay. There's one more in the chat there.
Okay.
One from
The current slide, coronal hole versus laboratory, VA versus distance, shows the velocity increasing.
That's Manisha's response to his question before.
That's what I was referring to for the earlier question. Yeah, so the Alfven speed is increasing with distance. Why does it increase with distance? So this speed is it's magnetic field over the density, and the density drops faster. So that makes it increase, actually. So the density falls faster than the magnetic field. So you get an increase in the speed.
And the actual last question was, does gravity play a role in the mechanics of solar corona heating? Question from Jeff.
Yeah, probably not. Gravity is a relatively weak force compared to other things. So the sun is huge, so gravity on the whole sun is important, makes the nuclear fusion in the middle, but it doesn't do much to the coronal heating. Yeah. Electric and magnetic fields tend to be much stronger forces than gravity. Like, think about, like, you can, stick a magnet on your refrigerator, but it's got the whole earth pulling down on the magnet, but the magnetic field is still enough to stick it to the refrigerator. So these things are much greater forces.
Well, I'd like to thank Dr. Hahn for spending the time with us, teaching us all about the sun and the wave heating. It's amazing stuff. That will conclude our meeting. Hans?
Knows anything about the Sea Stars telescope? Has any experience with it? I would very appreciate talking to you or contacting you.
I have
Sure. So we're going to adjourn the meeting. Thanks everybody online for joining. We'll see you next month. Take care.
Thank you.
Thank you.